So yeah, today we are gonna wind up all the concepts that we learned in this chapter, right? So the last topic that we did in this chapter was relative velocity, right? So we studied relative velocity and how is it different from how do we interpret relative velocity, right? So the last topic we did was relative velocity, right? So relative velocity is velocity of something in relation to something, some other velocity, right? So if you consider like a train moving with respect to me that I'm standing, so the velocity of train is, let's say, 140 kilometer per hour. So that is with respect to me, right? With in relation to me, that is just standing still and watching the train move by, right? So that is basically the relative velocity. So you can't have an absolute value for velocity. So what is absolute? Absolute is a universal value for velocity, right? You can't have a universal value for velocity of train, right? So for me who is standing and someone else who is standing here with me, the velocity of the moving train is 140 kilometer per hour, right? Now if I change the perspective, if I change the way of looking the train move, if I move inside the train or I'm traveling along the train, if I'm traveling in another train going in the same direction at same velocity, right? So for me this train is literally stationary, right? I don't see, if I see a certain mark on the train here, right, and I'm standing just parallel to that mark, right? The mark is in front of me, I'm just parallel to the mark, right? I'm just seeing the mark directly. So during the course of the motion, if both of the velocity do not change, right, both the velocity remain constant. So if they constantly move at the same velocity, which means that I'll never see the mark move forward or backward. It's just in front of me and it will remain in front of me. So it basically, we come to the point that for me that is moving on another train in the same direction with the same velocity, I'll find the other train to be stationary. The train will not be in motion with respect to me, that is traveling in another train at the same velocity, right? But if someone else is standing outside and watching the two trains go, the person can see both the train moving at a velocity of 140 kilometer per hour. So that is how perspective changes the velocity, and that is the main reason why we have the term relative velocity, right? Velocities are not absolute. Most of the things in the universe are not absolute. Most of the things are relative. We consider everything with relation to something else, right? So if I consider mass of something, right, if I say someone is fat or someone is thin, the most common example that I give to explain this concept. So if someone is fat or someone is thin, it depends on the way you're comparing the two person, right? So if there is a comparison between like a person with 120 kilogram and 80 kilogram, the 120 kilogram guy is fat, right? The 80 kilogram guy is thin as compared to the 120 kilogram guy. But automatically, if the 80 kilogram guy is compared with a 20 kilogram guy, then the 80 kilogram guy is excessively fat with respect to this guy, right? So everything in the universe, most of the things, like not everything, if I that will be totally wrong. Yeah, but most of the things in the universe are relative. So you can explain something with respect to something else. Everything in the universe, most of the things in the universe work that way, right? So there are very less amount of quantities. There are very rare quantities that are absolute. Okay, the values that we consider absolute. For now, let us say that velocity of light is absolute, right? But if you go on to study relativity and all those things, if you further your like interest in relativity and speed of light and all those things, you'll again come to find that this is not an absolute quantity. The velocity of light is also not an absolute quantity. It changes with respect to some changes in its atmosphere or some changes in the things that is happening around it, right? So that I'll not go in detail about it because it's like the standard of these kind of explanations is quite high, and it'll be very difficult for like you guys to understand it properly. Okay, so just for now, let us understand that velocity is relative. So we consider velocity with respect to something else, right? So what are the other things we did in this chapter? Let me go through it once. So we did acceleration, right? So what is acceleration? Acceleration is basically change in velocity upon time. So v2 minus v1 divided by total time, that is t2 minus t1. So this is basically, we represent it in this term. So this symbol is known as delta, right? delta delta. So we represent del v by del t. So that is acceleration of a body, right? So we studied this. So acceleration, if you simply want to know what acceleration is, it's basically how fast or how slow you're moving with respect to your speed like some time ago. Like let's say after like at a particular instant you're moving at a velocity of 20 kilometers per hour, right? And after, let's say, 10 seconds, 10-second interval बाद, you find yourself moving at a velocity of 40 kilometer per hour. So which basically means in like a time span of 10 seconds, you change the velocity from 20 to 40. So this will be basically your acceleration will be 40 final velocity by initial velocity v2 minus v1 divided by t2 minus t1 is basically the time interval, right? So time interval is 10 seconds. So your acceleration will be 20 by 10, that is 2 kilometers per hour. Sorry, it's not 10 seconds, this is 10 hours, right? So it will be 2 kilometer per hour square. So you're changing at this velocity, you're changing at this acceleration, so you're changing your velocity at this rate, right? So this can be negative as well. So you can have like initial velocity of 40 and after 5 hours your velocity becomes 20. So now your acceleration will automatically be negative. And this is this, as I termed it, I coined it, like it's like the common term that is used in every book is deceleration, right? For you, I studied with I like mentioned deceleration or even retardation, right? So you can also call it retardation. So basically it's your velocity is decreasing over time, all right? So that is deceleration or retardation. Then excuse me, we did the three equations of motion, right? The three equations that are absolutely essential for defining the motion of a body. So we can actually define it with either of the three, but all these three are actually very important. The first equation was v equal to u plus at. So v is the final velocity, u is the initial velocity, a is the acceleration of the body, and t is time. So if the acceleration is 0, if your body is not changing its velocity over time, so if you're not experiencing a change in velocity, or you're like purposely not changing your acceleration, right? So if you're not increasing or decreasing your velocity, then this v will be equal to u, because this thing entirely becomes 0. Since acceleration is 0, 0 into any number is 0. So your final velocity and initial velocity will be 0, which clearly means that the velocity that you were traveling initially, the same velocity you are traveling at the end of the or the time span, like the time span of consideration, right? If you are considered like 10 hours of motion, even after 10 hours your velocity is exactly the same. So that is the first equation of motion, v equal to u plus at. Second equation is s equal to ut plus half at square. So s is basically the displacement or the path length traveled by the body, right? U is the initial velocity, a is the acceleration, and t is the time. So this gives you the path length of the body that is traveling at the initial velocity of some value. And last one is v square equal to u square plus 2as. So v is final velocity, u is initial velocity again, a is acceleration, s is displacement or path length, right? So these are the three equations of motion that we did. These are absolutely very important. These are like this will come everywhere in physics. Like if you go for Newtonian, the Newtonian physics, that the basis of physics, right? Basis of motion, basis of kinematics, basis of dynamics. So all these equations are absolutely important. Like there's no equation that is more important than this and more basic than this, right? So everything can be derived from this equation. Everything can be a subordinate of these equations. It's like absolutely very important. Okay, so these are the three equations of motion. What else did we study? I think we studied the velocity time graph, acceleration time graph, right? So we studied the velocity time graph in detail. So we studied the velocity and time graph. So this is the velocity in the y-axis, time in the x-axis. You can interchange the axis, no problem. You can take time in the y-axis and velocity in the x-axis, doesn't matter. So we studied different cases. So this is one case. So the velocity value is not changing. So let's say 5, 10, 15, 20, 25. So this is 25. So 25, it's not changing over time. So you're moving at a constant velocity, right? You're moving at a constant velocity. And there was another case as well. So this was the another case. So this was basically the case for uniform motion, uniform velocity, or uniform motion. Uniform motion means velocity is not constant, but it's changing at a uniform rate, right? So for 1 second, if the velocity, like in 1 second, the velocity is changing at 4 meter per second, means for the next second as well, the velocity is changing at 4 meter per second. So for the third second as well, it's changing at 4 meter per second. So this is the graph for uniform motion, where the velocity is changing uniformly, right? It's changing at a constant rate, right? So and the third case is this one. So your velocity is decreasing over time, right? So basically velocity at this point is higher than velocity at this point. So over time, over a particular time, the velocity is decreasing. So this is basically a case of retardation, right? Retardation. So the one with uniform velocity, was a case of acceleration, right? The body is accelerating, so the velocity is changing. It's increasing uniformly. So I said I like use the term increasing uniformly, right? So it's not remaining the same, it's increasing at a constant rate. So basically velocity at this point, so this was the graph for uniform velocity, right? So this is velocity, this is time, this velocity. So velocity was increasing constantly, which means at this point the velocity is like 1, this point the velocity is 5, this point is velocity is like 10, right? So velocity is increasing, so this is a case of acceleration. So this is how you come to combine the things that you studied. So this is basically a case of acceleration, this is basically the case of retardation, right? So these were the things that we studied. And what next? And okay, this was there. Then we understood the concepts of distance and displacement. So what is displacement, what is distance, how is it different from each other, right? So distance is basically the total path or total path length traveled by a body. So if it's a hilly terrain, this entire thing, you have to consider this entire thing, so that's distance. But the displacement in the same case will be this thing. There's the shortest distance between any 2 points. So displacement is the shortest distance, and distance is the total path length of the body. So distance is a scalar quantity, it should be very clear, and displacement is a vector quantity. This also should be very clear. We know what is velocity. Velocity is displacement upon time. We know what is speed. Speed is distance upon time. So you should know about this. Velocity is a vector quantity. Speed is not a vector quantity. Speed is a scalar quantity, right? So yes, we did this. We discussed about what is a scalar and what is a vector. So I think you should be clear with what is scalar and vector by now. So scalar quantities are quantities that just have the magnitude. So that they just define the value of something, right? They don't give any idea about the orientation or direction of their the direction of whatever it is, right? So if I say mass of my mass is 50 kilograms, so I just get an idea about my mass, that is 50 kilogram. I have no other information about my mass, right? It's not acting to the right, it's not acting to the left, it's not acting upward, downward, whatever it, right? So we just know that it just gives us the magnitude value. And there is something like vector quantity, like I applied a force of 5 Newton to shut the door. So I know the direction now. So I applied the force in a direction where the door is shutting, right? So force is a vector quantity. Mass is a scalar quantity, right? I have my body temperature is 104 degrees Celsius. I have a high fever right now. So that is a scalar quantity. So my temperature is 104. So I just know there is a magnitude. There's a magnitude magnitude value of temperature, 104 degree, right? But I don't know where the temperature is acting, right? That it doesn't make sense. Like the statement itself doesn't make sense where the temperature is acting, right? So we can't tell that. So that's a scalar quantity. And another example of vector quantity would be displacement, right? So go 40 meters east from my location. I'll just go 40 meters east from my location. So I'm telling you, just go 40 meters from my home in the east direction, right? So you'll reach a particular destination. So that is displacement, right? So this is basically the summary of this entire chapter. So these were the most important things in this chapter. So if you guys have any doubt regarding this chapter or any other topic, just send a message to me, or just drop a comment down below. I'll reply to you on your comment, or I'll just link my email ID in the description. You just email me, right? And I'll try to respond to you as soon as possible. So try to revise these things once again. So this chapter is absolutely important for like physics as a whole, right? So try to be thorough with this chapter. So that's all for today, guys.